Good morning, everyone. I have to figure out the time. So welcome to this i2X first session. It's the first session this year, I believe. We'll be talking about power quality and protection requirements today. Just as a reminder, the first half of the meeting will be recorded and may be posted on the DOE website or used internally. If you don't wish to have your voice recorded, please do not speak during the call. We'll have Slido platform open for those who wants to provide written comments. If you don't wish to have your image recorded, please turn off your camera or participate by phone. If you speak during the call, use video connection, you are presumed to consent to recording. All right, so as always, I have this polling question here. Please go ahead to slido.com, use the event code first9, and tell us what industry you are representing. It helps us to shape future meetings and also understand our audience better. Right, so for those of you, I hope there are no new people on the call, but those maybe that are joining first time anyway, I'll just remind what are the key goals and outcomes of i2X first. We are here to facilitate understanding and adoption of new and recently updated standards that are relevant for existing and new interconnecting wind, solar, and battery storage plants. The forum convenes industry stakeholders to enable practical and more harmonized implementation of the standards. The presentation portion of the meetings is recorded and the presentation slides will be shared. And additionally, the leadership team is producing a summary of all these meetings where we are capturing recommended best practices, challenges, gaps that require future work. And you can also access the summary of all previous meetings all within one document. All right, so for the leadership team, we have Cynthia Boswell from Boston Government Services. She's contractor with DOE Vito. And then we have Robert Reedy. He is a contractor with DOE CETO. Will Gorman from Lawrence Berkeley National Lab, Jens Boehmer, from EPRI, myself, Julia Matevosian from Energy Systems Integration Group, and Ryan Quinn from Elevate Energy Consulting. Just as a summary of the last meeting, we had a meeting, the title, we had a meeting on voltage control requirements. So we spoke about clause 5 of IEEE 2800. So Jens presented on that, then MISO presented phase 2 of the IEEE 2800 2022 adoption efforts. Patrick Dalton spoke to that. BPA presented their voltage control strategies, and then we had Q&A and structured discussion around IEEE 2800 Clause 5 versus FERC Order 827 requirements, and also implementation of reactive power voltage control requirements. You have a meeting summary and recording and presentation posted on the DOE i2X first webpage. Once we share the slides, you can also have a direct link. One other thing I wanted to mention, we're actually planning a follow-up. We were planning a follow-up meeting on voltage control requirements in January. Unfortunately, it got moved. But we're still planning to hold it sometimes in April. So there we'll talk about, people requested about further conversation about voltage control requirement implementation and also VARs at night. So we'll talk about that. So just a few key themes from the last meeting. As I said, we talked about Clause 5 adoption. This requirement can help clarify and refine existing voltage control requirements and aid reliable design and operation of inverter-based resources going forward. Sometimes conflicts between FERC Order 827 and Clause 5 may result in not fully leveraging capabilities of inverter-based resources, particularly this related to rectangular versus triangular shaped curves. This may be leading to underutilization of IBR reactive power capability and may result in costlier transmission reinforcements than are necessary. reference point of applicability for voltage control, we talked about that. And so this is the most common place where the voltage is controlled. So like if it's chosen to be a POI, then this is where the voltage control is applied for BPS connected inverter-based resources. And clause 5 of IEEE 2800 actually includes specifications for performance targets for this type of control, including reaction time, maximum step response time, and damping ratio. And then we also talked about selection of droop and deadband settings, that sometimes it makes sense to base it on local bulk power supply system needs and transmission operator voltage control practices. And choosing it kind of in this customized manner can help to improve grid reliability and stability. All right, so talking about upcoming i2X first meetings. So we are now in February talking about power quality and protection requirements. In March, we'll have another hybrid, so in-person and online event, as we had during fall E6 Spring workshop. Sorry, we had one during E6 fall workshop. Now we're going to have one during E6 Spring workshop. This is going to be a half-day event where we'll continue discussing draft of 2800.2, and we'll be talking about conformity assessment during post-commissioning stage. So after the plant got commissioned, how do you ensure that the plant is conformant with applicable interconnection requirements, including 2800? And then, as I mentioned, in April, we'll come back to reactive power voltage control requirements and have this continuation session that I mentioned in the beginning. And then after April, we'll continue with i2X first sessions, focusing more on implementation of interconnection requirements. So if you already have defined interconnection requirements or adopted IEEE 2800, how do you ensure that the plants actually comply? So to sign up for i2X first meetings going forward, there is a link here, and then also there is a link to where the meeting materials, recording, and everything is posted. So for the half-day workshop, just a little bit going into details, we'll talk about, as I mentioned, post-commissioning conformity assessment. The workshop will cover the assessment process after the plant got commissioned, following along the lines of IEEE 2800.2 subgroup 5 scope. The agenda is available under the link below. It's in person and online. If you're online, it's a free participation. In person, it just has a registration fee to cover the costs of, of the venue. And this is held before E6 Spring Technical Workshop, and I provided a link to that one as well if you are interested. Here are the links for registration for the main workshop and i2X first. All right, so going to the agenda, I've already talked through my 10 minutes almost, and then next we'll have Manish Patel from EPRI talk about IEEE 2800 Clause 9 protection requirements, and then Dave Mueller from Enernex to cover Clause 8 of 2800 on power quality requirements. Then we'll have some time for Q&A for the presenters, and then continue on with a structured discussion led by me, and we'll have some in-depth questions about production requirements and power quality requirements. So please be active, participate in the discussion. Right now, go to Slido, indicate what industry you're representing, and we'll just go ahead and get started. Just some code of conduct here, just be respectful to everybody, and post constructive comments and questions. That's all. And with that, we move on to Manish's presentation. Manish, you can go ahead and get started, and please introduce yourself.
All right. So I am Manish Patel. I'm with EPRI. I was one of the vice chairs of the 2800 standard working group. So let me start sharing my screen here. It appears on the screen, right? All right, so this is a little difficult topic to prepare a presentation for, because the protection requirements and the standard are pretty brief. I could just, in simple words, say that the standard requires that any protection applied within the plant shall not interfere with the plant's ability to ride through the voltage and frequency disturbances as specified in the standard, full stop, and we are done with protection requirements. But we did add a little more details in the standard. But again, I think when you read about 2 pages worth of content in the standard in clause 9, you can walk away with the conclusion that I just mentioned. So let me try to elaborate a little bit more on this. Before we get into the details, I'm going to mention interconnection system a little bit during next 10-15 minutes. And I thought it would be great to make sure we all on the same page. So the standard defines interconnection system. I'm showing that on my screen here with the red pointer as the tie line between the point of measurement and point of interconnection. So IBR tie line or interconnection system are same thing. So we'll talk about interconnection system protection a little bit. So want to make sure that we are on a same grounds as to what is the meaning of interconnection system. Obviously, you have heard this before many times. Most all requirements of the standard apply at the point of measurement, that is high side terminals of the main power transformer. And protection requirements, we did not really spell it out. Wherever the protection is applied in the plant, they need to follow the standard and make sure that those protection does not interfere with the right through capability of the standard. All right, with that said, as I said, standard does not require specific type of protection. I think the reason we ended up writing this statement very clearly and repeated it quite a few times is because if you look at IEEE 1547, then I think it requires DER to trip for certain voltage deviations of given duration or frequency deviations of given duration. But we want to make sure that these are IBRs that connect to transmission, sub-transmission system, and there is no requirement like 1547. The standard does not say that the IBR has to trip if the voltage stays below certain magnitude for certain duration or frequency remains below certain magnitude for certain duration. Standard does not require any type of protection. It is up to the plant designer and the OEMs to decide which protection is needed to protect their equipment and then make sure that that protection is not going to limit the plant from meeting its right to requirements of this standard, right? Okay, so that's the first bullet there. If protection is applied, shall allow IVF plant to meet its right to requirements. We did spell out a little bit of details for voltage, frequency, ROCOF, overcurrent protection, and I will show you that in next few slides. Unintentional islanding. If not permitted by the transmission, then protection shall be implemented in accordance with the requirements of the TS owner. So most transmission entities out there would like some sort of anti-islanding protection. Most OEMs may have their own ways of detecting an island that is built into inverters and tripping for it. Now, some entities out there may rely on built-in protection within the inverters, whereas there are some entities out there that think that no, they would like to prefer, a transfer trip-based anti-islanding protection, and they have a little more control over it. So we just say, well, if the transmission owner requires anti-islanding protection, then implement it according to the requirements of the transmission owner, right? And then interconnection protection, we were not going to go and spell out how the tie line is going to get protected. Some tie lines could be short, some tie lines could be long, some prefer differential, others prefer distance. The list can be very long. So again, we simply say that any interconnection system protection just follow the specific requirements by transmission owner. All right, so I'll take you into a little more detail, but I think at the end of next 10 minutes, you will you will feel that this first slide kind of outlined expectations very clearly. So frequency protection, as I mentioned earlier, unlike 1547, this standard does not require that the plant trips for some weird frequency deviation for some long time duration, right? If the plant needs to protect itself from frequency disturbance, then they just need to make sure that that protection is set so that the IBF plant meets the right requirements of the standard. And then the last bullet is more of a just make sure that any protection applied within the plant is coordinated with any frequency protection on the transmission under frequency load shed system, load shed program usually implemented on transmission too. There is no point in tripping generation before tripping a load, right? So very basic requirements there. Roke off, again, as I mentioned earlier, standard does not require that if the roke off is more than 5 hertz per second, then the plant shall trip. It simply says that if the roke off is at least a roke off up to 5 hertz per second, the plant shall be able to ride through, right? So if plant if it's necessary to protect the plant and any equipment within the plant from severe roke off, then just make sure that whatever mechanism is chosen to declare that the roke off was higher than certain threshold, it allows the plant to meet the right requirements of the standard. The last bullet is sort of important. Frequency measurement itself, right? Forget about roke off. Frequency measurement itself needs to be done over few cycles. There are enough literature out there that talks about how to reliably measure frequency. So we call that out again. Roke off should be based on change of frequency averaged over sufficient time so that you can reject bad measurement caused by distortion and transients. All right, so then AC voltage protection. Again, any applied protection shall allow plant to ride through or meet the ride through requirements. If voltage protection is applied, then it should be coordinated with any protection, equivalent protection that transmission owner might have in the area, and then obviously any undervolted load sharing scheme. The last bullet, important, instantaneous overvoltage protection used within the plant shall use filtered quantities. Now, the reason for this was, unfiltered quantities might have some transients that might trigger instantaneous protection. If you use filtered quantities, then some of those transients are filtered out, and then the protection becomes more reliable. So to reduce the possibility of misoperation, the standard says use filtered quantities in any instantaneous protection. A few more details. Any instantaneous overvoltage protection that has possibility of disrupting the plant output, complete plant output, shall use at least one cycle measurement window. So this is if someone decides to apply instantaneous voltage protection at the point of measurement, right? So if that protection element misoperates, you risk losing the entire plant. So we made sure that for that level of protection, where the risk is the loss of entire plant because of misoperation, then that instantaneous voltage protection shall use at least one cycle measurement window to reduce possibility of misoperation from transients and whatnot. Now, the second bullet here on the screen is also fairly important. Any instantaneous voltage protection that is applied within the inverters or the wind turbine generators to protect, for example, IGBTs, well, it needs to be coordinated with the transient overvoltage right through capability specified in the standard. Be coordinated with any surge protection that can suppress some of those transients applied in the standard, right? So we have written up some of that guidance in the standard that if it is used, it needs to be coordinated with everything else in the plant. Next one, AC overcurrent protection. So again, this is applicable to phase. If the protection is detecting overcurrent on a phase A, B, or C basis, or it's detecting overcurrent on a, say, positive sequence or negative sequence quantities. Again, the standard does not say that something in the plant has to be protected by overcurrent protection. Right, but the standard says if overcurrent protection is used within the plant, either at the plant level or individually in the inverters or wind turbine generators, then that protection shall be set such that it does not limit the facility from meeting its right through obligations based on the standard. So fairly simple. A little more details, instantaneous overcurrent protection used within the plant shall use filter quantities. Same reasoning as I mentioned when we were talking about over voltage protection. It allows some transients to get filtered out and allows the protection to become more reliable. Any instantaneous overcurrent protection that has possibility of disrupting the output of entire plant. So anything that is applied at the POM, for example, or on a collector bus, another example. And if it misoperates, that means the entire plant could be lost. Well, that should use or shall use at least one cycle measurement window, reduce any misoperation from transients and stuff like that. The AC overcurrent protection obviously needs to be coordinated with any similar protection that is used by the transmission owner on the transmission system. Unintentional islanding, as I mentioned earlier, most transmission entities out there today would like some sort of anti-islanding protection in place. Some may allow or some may rely on the anti-islanding protection that is built in the inverters or the wind turbine generators. And some may require transfer trip based protection. So the standard says any islanding protection used by units or the plant shall not limit plant's ability to ride through. And then if islanding protection is required by the transmission owner, then that protection shall be implemented as specified by the transmission owner. So then this is last point of this presentation, interconnection system protection. So this is the tie line between the point of measurement and point of interconnection. As I mentioned, that tie line could be long, could be small. There may be other IVF plants on that tie line. And the protection starts to become quite detailed, right? At that point, we're talking about 115, 233, 45 kV transmission lines. And all those transmission entities out there have different philosophies on how they protect the transmission portion of the plant. So we in the standard did not go into a whole lot of detail about specifying the protection for the interconnection system or a tie line. We simply said that the plant shall implement protection in accordance with the requirements of the transmission owner. Some owners might prefer differential protection. Some transmission owners might prefer simple step distance based protection. There could be other options out there. So the standard simply said, follow the instructions provided by the transmission owner. Protection shall be coordinated, right, with the transmission system protection. This is no different than setting any other protection out there on the grid. There has to be proper coordination and layers of protection. Standard calls for that. Protection schemes, again, whatever is implemented shall not limit plant from riding through the requirements of the standard. Exceptions fall on the tie line itself. Well, there is no point in riding through a fault on the tie line, right? The plant is eventually going to trip no matter what. Protection within the plant, if the collector bus is faulted, well, there is no point in riding through. So there are some exceptions like that included in the standard. And I think that is my last slide. Do you want to do Q&A now or?
No, we'll leave it after.
All right, thank you.
Thank you, Manish. All right, thanks, Manish. We'll move on to power quality clause of 2800, and we have David Mueller from Enernex on the line with us. Before you start, I just wanted to remind everyone to go to slido.com, use the code first9, and indicate which industry sector you're representing, and then afterwards we'll also use Slido for Q&A and for discussion if you don't want to speak up. All right, so without any further ado, Dave, go ahead and share your screen, and please introduce yourself.
All right, good morning, everyone. My name is David Mueller with Enernex. I'm coming to you from Knoxville, Tennessee this morning. I'm going to talk about power quality standards for IBR plants. Most of my focus is going to be on, you're seeing my slides okay, I guess. And so
Yes.
I'm going to talk mostly about 2800 as Manish did. I'm going to talk about the power quality sections in 2800. There's really only 3 of them. So we'll talk about voltage fluctuations, harmonic distortion, limitation of overvoltage contributions. I'll also, since I'm involved with 2800.2, talk about some of the things that we're working on that I think improve our situation for harmonics, and highlight a couple of those aspects that I think are going to survive the draft stages and I think are going to be a big improvement. And then I want to finally leave you with, I have a lot of experience with working with the actual plants and problems at the plants. So I'm gonna list what I think are the most common problems that we need to worry about. And most of the plants don't have harmonic problems. So I want to be sure I emphasize that more than once today. So let's get into it. So 2800, adopted 2022 now, so it's been out for a few years. The standard for interconnecting and interoperability of IBRs on the transmission system. The clause 8 was power quality. There are 3 parts to that clause, as I mentioned before: voltage fluctuation, harmonics, and overvoltage. So let's go through and look at those. First, voltage fluctuations. Manish made an interesting comparison with IEEE 1547, which is the DER standard. And this is another area where probably this is more important in the DER realm in terms of voltage fluctuations, because the IBR plants can have, I would say, more of a significant effect there. And right now, in fact, in our work revising IEEE 1547, we spent a lot of time talking about voltage fluctuations and rapid voltage changes. And it's probably not surprising, whereas we haven't spent much time on this in the 2800. So for frequent, what is frequent? Frequent is anything that's not infrequent. And forgive me, for infrequent would be transformer energization and other maintenance operations. So things that happen, I don't know, once a week, once a month, something like that. Whereas frequent would be daily types of things. If I tried to put a time on it, the standard doesn't really define it any more than what I've shown here. So in frequent, we want to have less than 2.5% voltage variation in RPA due to the plant operations. And capacitor banks is one of the things that can obviously step the voltage. As you switch into cat bank, you're going to raise the voltage. Infrequent rapid voltage change. Transformer energization is far and away the most important category here. This 12% requirement, I found out, actually came from the National Grid in the UK, but it was adopted by IEEE 1453, which is the flicker standard, and it is mentioned in 2800. I think that's not to say that the transmission system owner can, at their discretion, consider a more strict limit. But if you are a transmission system operator, consider the fact that you may have your own power plant and your own power plant equipment that would also need to comply. And for something that's going to happen very infrequently, this 12% number perhaps is allowable. But it's a very lenient standard, I would say. We do transformer energization studies, and I think most of the time the short circuit ratio is enough that we don't hit that point. Transformer energization, by the way, is what we call a point on wave phenomena, which means that depending on when the breaker closes, depending on the remnants flux stored in the transformer, you might get a different answer for every simulation. We typically, when we do the studies, we do 100 statistical shots at different timings to see what's the worst. Flicker is the light variation that one would see due to voltage variation on the system. The history of flicker is that it was established by experimental means to determine what people's perception was to voltage variations on 60-watt incandescent light bulbs. Well, we don't have any of those anymore. We have LEDs. And so there's a lot of discussion about the fact that the limits probably should be something different. I don't know how they should be different. The flicker meter should probably be different in the way that it senses flicker, but as of right now, what we still have in the industry are these limits based on 60-watt incandescent bulbs. We've got both 10-minute values, the so-called short-term flicker, and 2-hour values. Generally speaking, we like the values to be less than 1.0 per unit on the flicker scale. So at 1.0, we're saying people are going to start to notice the lights to flicker, and we want to keep it below that. And so the planning limit for transmission systems is generally 0.8 or 0.6, depending on voltage levels. We're not going to allow a plant to use that whole limit. We're only going to use a plant to use a portion of the limit. We've done flicker evaluations for plants. We never get close to these values. The operation of wind turbines, the operation of inverters is much more smooth than this. So flicker is not normally any sort of an issue. We have seen it with older style equipment on weaker systems, but that's not the norm. So now let's talk a little bit about harmonic distortion. In 2800.2, I think we spent almost all of our time talking about harmonics, and I kind of wondered why, but then I realized we've only got 3 things to talk about anyway. So this has been the lion's share of our discussions, harmonic distortion. And I got this silly picture on here, and I've used it for years. And what I've said when I've used these pictures is we need a cooperative effort, because we've got the grid connected to the IBR plant, connected to another IBR plant, connected to another industrial source, connected to a data center, connected to people's homes. All those types of interactions come into play here when we talk about harmonics. That the characteristics of the grid affect the IBR plant, the characteristics of the IBR plant affect the grid. And so it gets to be a relationship that can be somewhat difficult to study. And so we focus some attention on the studies requirements in particular. But in 2800, what we have are limits. So let's talk about the limits that we have in 2800. Well, before I do that, let me say that we had a lot of discussion. Should we be limiting harmonic voltage or harmonic current? And harmonic voltage is what we care about. It's what we want to limit on the system. It's the power quality metric that's important. And it's used for larger projects where there's a lot of engineering work that can be done and a lot of large system studies that can be done where we have a lot of engineering. And it's used around the world. But there are some problems with harmonic voltage limits. First of all, it's hard to determine what a plant would cause on the harmonic voltage distortion. If we're below the limits, then we're fine. But what if the system is already above the limits? And that is the case. I'll talk about this a little bit more later, but many of our systems in the US currently exceed the IEEE 519 recommendation for harmonic voltages, particularly 230, 345 high voltage systems exceed the 1.5 and the 1% limit. So if we're already over the limit, then are we going to ask our IBR plants to filter to get down to the limit, or how are we going to establish that? How are we going to determine what contribution the plant's making to the limits? Are we going to shut things off, turn things on? Harmonics are time varying, very difficult to apply harmonic voltage limits. On the other hand, harmonic current limits in theory are fairly easy to apply. I mean, you just go measure the harmonic currents. If we're below that, then we're good. That was a familiar concept to utility power quality engineers in the US who were familiar with IEEE 519 harmonic standard, which is actually very popular around the world because it has current limits that are fairly easy to apply. And so it provides an easy screening. But there are problems with current limits. And the problem is, what if I'm absorbing current from the system? How do I deal with that? What if I'm filtering current from the system? How do I deal with that? How do I deal with the direction of currents coming from the grid and to the grid and all of that type of thing? So that there would be problems both ways. First of all, we set for harmonic current limits. As I said, we got limits in a table, and we can go out. We can actually measure post generation. When we get the plant, we'll typically go out for a couple of weeks. We'll install a monitor. We'll measure. We'll run the statistics, and we don't have to meet the limits all of the time. What we have to do is meet the limits 95% of the time. We have to have a cumulative probability 95% level that meets the limits. So we can exceed the limits part of the time, but 95% of the time, the values that we record, we have to meet these limits, and these limits are in percent of rated current. So if it's a 200 megawatt plant, then perhaps we'll use that as our base rating to apply these percentages. We also use an interesting definition where we apply not just harmonic frequencies, but interharmonic or all frequencies. So we take the RMS value and subtract the fundamental and do the orthogonal relationship, and we come up with the TRD definition that way. This was first proposed in 1547, and I think it's a good definition, and it's actually even one that IEEE 519 is considering for its next revision, as opposed to current total harmonic distortion, which depends on how much fundamental you have. So anyway, most plants are going to meet these limits. These limits are very relaxed from what it was from 519, where we have percentages of a percent that had to be met, and we were finding that we were getting in the limits in the milliamps that we couldn't even measure accurately. And so the effort here was to make limits that were reasonable, limits that we could reasonably measure, and oh, by the way, limits that can be met, because the IBR plants are generally fairly low sources of harmonics, generally can meet these limits, and we're pretty much done. We can show that it's not causing an effect. There are, however, a lot of notes in the standards, and some of the notes I like and some of the notes I don't like. The first note is one of the ones that I don't like. The current distortion limits shall be absolute, inclusive of any harmonic current due to the harmonic sources in the transmission system and also the harmonic current due to the IBR plant. The reason I don't like this is I ask myself, why do I have to be responsible for currents coming from harmonic sources that I don't control? But that's what it says. So it doesn't matter whether I like it or not. That's what's in the standard. An example of something that I do like is the third bullet, where it says an IBR plant shall not be subjected to these limits if the harmonic currents do not cause a problem. They do not cause the individual harmonic voltages to increase. Okay, so basically, let's not worry about things that don't matter. So if we've got a high 11th harmonic current, but we find out we don't have an increase in 11th harmonic voltage, then we're still okay. So I think that's an important exclusion, if you will, to be considered. And there are some other ones, and I'm not going to go through all those today. What about harmonic voltage distortion? Well, first, the standard says this standard does not specify harmonic voltage distortion limit values, period. But then it goes on and it says the transmission system should specify voltage harmonic limits. So in other words, we're not going to set forward the limits in the standard, but the transmission system owner should set his limits, okay? And they should specify such limits. And then if they set the limits, we can talk about whether or not we want to even deal with the harmonic current limits, and we can talk about how we're going to remedy problems. What I want to suggest is that if a transmission system operator in the US does establish harmonic voltage limits, I will be very surprised if they do anything but go to IEEE 519 2022 and take those harmonic voltage limits straight from that standard, because that's what they're held to. That's what they're held to. So I'd be surprised if they would go anything different. There are problems with those limits, as I mentioned earlier. The fact that some places don't meet those limits currently. So this is an interesting clause. Let's talk about overvoltage contribution now. So there's limits of overvoltage contribution. So, this is not as big a deal as in 1547, where a lot of times we're worried about grounding and ground sources and neutral voltage rise and things like that. We don't typically have that with the typical plant. That usually the typical plant has a 3-winding transformer, delta ground, Y ground, delta Y ground, so that the Y ground windings provide a ground source either to the wind plant and or to the transmission system, so that we don't get neutral voltage overrise due to single phase faults and things like that. So we're talking more about load rejection criteria and things like that, but you'll notice in 8.3.1, this requirement shall not apply to situations where we become isolated from the transmission system. So the interesting part about the main clause is the curves referred to do not necessarily imply protective or action or control action. Okay, they don't imply that. And there's another sentence where it says we want the inverter manufacturer to design that in their equipment. My experience is the inverter equipment manufacturers, if you tell them that they can't produce those overvoltages, that's where they're going to set their trip settings. That's where they're going to set a self-protective overvoltage trip setting, because that's the best way they know to ensure against that. So if we look at the limitation of instantaneous overvoltage, the power quality says that the plant should not cause instantaneous magnitudes at the RPA to exclude the values in table 14. Table 14 actually comes from the ride-through requirements of the plant. So on the one hand, we're saying we've got to ride through these voltages and not trip. But on the other hand, we're saying we can't cause voltages of in excess of this. If you believe me, which is to say that the inverter manufacturers are going to try to comply with this by setting trip limits, then this kind of implies that they're going to set their trip limits identical to this table, because you can't both ride through and not trip without being right on the limit specified there. I think it's a little interesting. The other requirement for cumulative comes from the graph, which shows an example of how this is calculated over time. This is basically trying to replicate what's going to happen in a surge arrestor as far as energy, and to ensure that arresters don't have a problem with these overvoltages. This same chart came from 1547, and in the recent revisions to 1547, a lot of effort was put into explaining this graph much better, and I think that'll be a big improvement when 1547 does get published, which I expect it probably about in a year from now. Cumulative overvoltage is another trap. Now we're talking, actually here we're talking RMS. We're talking not instantaneous, we're talking RMS. We're not talking about things on top of the wave shape. We're talking about RMS values, primarily speaking here. Although interestingly enough, the graph shows subcycle cumulative duration. It says we should calculate RMS over a cycle, but then it gives a limit for subcycle. So I'm not sure about how to apply that, but I know that for the multiple cycle events, it's pretty clear. We're gonna do one cycle windowing. We're gonna calculate the cumulative amount of time over a 1 minute period that we're above a certain voltage level, and we gotta stay below that. So let me talk a little bit about some of the things we've been working on with P2800.2, which is the verification of plant performance to 2800. Harmonic studies are very challenging, as I mentioned, because we've got various interactions going on where the grid can affect the IBR and the IBR can affect the grid. So the basic formulation is that we got to get away from a typical harmonic current source model, which is not accurate, does not reflect the impedance contributions of the inverter. And we've got to go to a more sophisticated representation where we have either a multiple frequency, either Norton current source equivalent or a Thevenin voltage source equivalent. Now, if I have one, I can easily calculate the other one. So I don't have to get hung up on which one that I have. It maybe experimentally might be easier to just determine this from a Norton source. Maybe from a heuristic stance, it might be better to think of these voltage source converters as voltage sources of harmonics. But either way, the mathematics are identical for the studies, and we can work with that. The problem with this representation was there were no sources that we could find in the industry that told us how to do this. And so I challenged the group that if we want these presentations, we need to give the OEM some help. Some of the wind turbine manufacturers in particular had very good ways of doing this. They did a lot of laboratory work to develop very good models, but we needed it for the industry at large. And so I want to call out the efforts of Amir Kazemi, who is now with NextEra, and also Dr. Wilson Zhu from University of Alberta. The two of them brought both an industry and an academic perspective to this problem, and we've described fairly at length what the equations are, how this should be done. And I think that when that's published in 2800, that will offer us a chance to have better harmonic models of these equipment so that we can get the right answers. Harmonic studies are all about getting the right answers. If we get too conservative answers, we end up putting harmonic filters in everywhere. And actually, we find from experience we don't need harmonic filters most of the time. We're also talked quite a bit about when should we do harmonic studies? Should we do harmonic studies for every IBR plant, or are there high risk plants? And right now the draft has settled on high risk plants. So in other words, there are some plants, perhaps studies don't need to be performed in advance. Maybe some plants that don't have much of a risk factor, we're okay with building them and doing a post-generation measurement campaign, let's say, just to show that everything's okay. If you want to know what the high risk plants are, let's look at these bullets real quick. If it has a significant T line or certainly an underground cable, any offshore wind plant is high risk. If we have a shunt capacitor bank, that introduces a resonance phenomena that we need to look at. If it's a very big collector system, really any large wind plant probably should have a harmonic study done. Very large IBR plants where we have a low short circuit ratio. We tried to define this, we tried to describe this, we tried to talk about the size of the plant, and we just could not come up with how do we justify whatever either short circuit ratio or size that we put in there. So we left it kind of open. Project, if it has a high background voltage harmonic, if we're already over the IEEE 519 voltage limits, it might be nice if we have actually a pre-installation harmonic survey that shows us what we get before we even go there. That might tell us that, hey, this isn't an area where models are going to help us understand what the impact of the plant's going to be on the grid. And then if we have an IBR unit that's got negative damping and some harmonic frequency range, well, then we want to make sure we don't have that resonance condition, because we don't want to have that problem. I'll show an example of that in a moment. And then finally, it's kind of a catch-all, and I'm guilty of writing this, so we probably will write it different than this in the final version. But plants where the developer wants to do a study because they want to manage their own risk. I think we don't want to dissuade anybody. I do harmonic studies for a living, so if somebody wants to do harmonic studies, then I'm all for it. But I also really want to see the industry go forward, and I don't think that in all cases really harmonic studies are necessary. And so this gives us some guidelines. All right, I'm going to leave you with a little exercise here where I would like you to think about what you would consider are common harmonic concerns at IBR plants. And if you don't know, I'm going to show you what I think the 4 are. But I'll give you a moment to think about that and maybe write down one of your answers, and we'll see if you match one of the 4 answers that I put up here on the screen. And these are not necessarily in any particular order, although I'll start with number D first. So, okay, survey says number first common harmonics concern IBR plant: unit, turbine, or inverter transformer failures. Now, transformer failure, I'm a guy who likes to say a transformer failure is a transformer problem. The transformer needs to be designed considering the fact that it's on a converter. It's going to see harmonics. It's going to see high frequency harmonics. This is a measurement from a wind plant where we actually measured. You can see the pad mount transformer. It's de-energized at the moment. We're hooking up our probes. We actually see higher voltage harmonics than we see current harmonics at the 690 volt level. The bottom graph is current and the upper graph is voltage. This is fairly common when you measure inverters at their output. You'll see a higher amount of distortion on the voltage. It kind of falls in line with the voltage source converter or voltage source of harmonics, if you will. But can that affect harmonics? Well, can that affect transformers? Well, if the electrostatic shielding isn't what it needs to be, if the insulation isn't what it needs to be to handle these types of considerations, then that might be taxing. But, for this report and other reports, what I've said is, was the manufacturer of the transformer told that it was going to be used on a wind turbine inverter? Was the transformer manufacturer told that there were going to be harmonics, switching harmonics at 3 up maybe up as high as 6 kilohertz that it's going to be exposed to? Are they able to? Clearly, many facilities are able to design transformers and design transformers that meet these criteria, but some are not. The problems typically start as a high dissolved gas reading where there's something going on with the transformer and a failure occurs sometimes later. Sometimes it's been found that there was a problem in manufacturing where there wasn't a clearance, say, around the tap change mechanism or something like that. So it's not always harmonics, but certainly harmonics get blamed for it. And so I have to include it in my list of harmonic problems, these transformer failures. All right, so now let's move on to the next one. What is the next one that I call out as a common harmonics concern? Converter instability. So the story is always very similar on these projects. The project was running just fine. Then the vendor decided to push a new version of firmware into the controls of the wind turbine. And following that, the main transformer in the substation started making strange noises. Capacitor banks started tripping, other problems starting occurring. In one place, transformers on an industrial plant 20 miles away were making noises, singing these higher frequency harmonics. You can see each sine wave here shows what looks to be harmonics. But actually, if you look at these waveforms closely, you'll see that they don't actually repeat themselves every cycle. If you look at the peaks have a difference from cycle to cycle to cycle. And what that tells me is that the voltage here is actually an interharmonic. It's in between harmonics. And we can see as high as 40% distortion in these cases. I've seen about a dozen cases. I've seen cases with wind turbines. I've seen cases with type 3 wind turbines. I've seen cases with type 4 wind turbines. I've seen cases with full conversion wind turbines, as I said, and also inverters. It hasn't, for whatever reason, it hasn't been as prevalent in inverters as I thought it would be, because we seem like most of the major manufacturers of wind turbines had at least one case of this, to my knowledge. But inverters, we haven't seen as much of it. So I don't know if there's something different about the way the current controller loop that makes it a little more sensitive, but maybe we're getting past this problem of converter. What's going on here is that the controls are unstable at a frequency that the grid is resonant to. If we switch a capacitor bank in and we create this resonance, we'll get this phenomena. If we take that capacitor bank out, this problem will go away because we don't any longer have a resonance at that instability. So the two things have to line up. The converter instability has to line up with the system resonance condition. All right, getting on to the third one. Capacitor banks in our IBR plants causing resonance conditions. This is probably one of the most common ones. It's also very important because many plants use capacitors as a effective way to offset the reactive power losses in the transformer and the collection system to meet their to meet the reactive power requirements. But that capacitor bank introduces resonance considerations, and that resonance can cause a problem inside the plant, and or it can cause a problem on the transmission system at the point of interconnection, where it magnifies harmonic current levels. Recently, one plant that we were working with, they switched in the cap bank and things started making noises, and they burned up their AC unit inside the substation, and they had other failures of some of the converter electronics and other types of things. So these can be quite serious problems. So capacitor banks really need to be studied. Most of the time, the resonance are out of harm's way, but if the resonance is close to the fifth or close to the seventh harmonic, that's very typical for a transmission system background source, then that can be identified as a potential problem. So that's capacitor banks. One last one that I will highlight is the background harmonic voltage distortion levels is already over the limits. It's a pre-existing condition. It's not necessarily a problem. The grid's been living with that for years. Nobody's been complaining about it until we said, oh, we're going to go out and do a harmonic measurement at the plant. And oh, by the way, what we're seeing is that if we're a 230 kV system or a 345 kV system, our limit is 1.5% for the THD, and our limit is a minuscule 1% for an individual harmonic voltage distortion. In Europe, typical voltage limits for this type of thing in the IEC are 3 or 4% for high voltage systems. And actually in the UK years ago, they increased these limits because they recognized that they weren't driving 55, they were driving 70 mile an hour. So they ought to set their limits more where they're driving. And it's really more about how you apportion the limits at different voltage levels. And they decided to be more realistic. So in Europe, when they apply harmonic voltage limits and they have a limit of 3 or 4%, there is some headroom. There is some room for the IBR to cause some increase without being a problem. But with our limits, our IEEE 519 limits in the US, in many cases, we're already over the limit. There is no headroom. We're already in the hole in terms of what we're going to do. I just, when I try to convince 519 working group that I'm part of that we ought to change these limits, I said, hey, we've got a bunch of experience at a bunch of places where we just can't meet the limits, particularly the fifth harmonic voltage limit is typically a problem in a lot of sites. But anyway, the limits are what they are. They didn't get changed. And so this is a pretty typical example here. This is actually a site where if you look at the THD and you recognize that the limit is 1.5%, it might look like that we're not okay there because we're over the limit, but actually we only need to meet it most of the time, not all the time. We need to meet it 95% of the time. And it turns out actually that the 95th, this cumulative probability 95 value of this data was 1.45. So we were actually 95% of our measured values were 1.45 and below. So we could actually state statistically that we meet this limit for THD at this site. However, this same site was dominated by fifth harmonic voltage, which is often the case. And so now at the fifth harmonic voltage, our limit's 1%. So this occurs whether or not the wind is blowing, whether or not the wind is on. It's just a background condition. So if we want to meet IEEE 519 voltage limits, we're not going to be able to do it because of a pre-existing condition of the background voltage distortion. So those are my 4. I don't know if you, maybe in the discussion, if you've got ones that I didn't mention on here, let's talk about those as well. I just in summary like to say that the standards are evolving. We'll continue the discussions and the give and take on the standards. We got 2800 for our IBR. We've got 519 is now harmonic producing loads, so it no longer applies to generation equipment. That was changed in 2022. But it's the only harmonic voltage standard that we have, and so it's still significant in our realm for harmonic voltages. 1547, We talked in 1547 about whether we ought to increase the harmonics to beyond the 50th harmonic, because we're seeing some places where the higher frequency switching is causing issues. We decided not to do so. Too much trouble testing that, not considered enough of a common problem yet. Most wind and solar inverters are actually pretty good power quality citizens. They're actually very slight sources of harmonics. That's because the converters are multi-level modular converters that are designed to have very low harmonics. Yes, they have high frequency switching noise, but by the time we see that impact up on the grid, up on the transmission system, it's a very slight source of harmonics, and not so. Most projects, we don't need harmonic filters. There are other countries like Brazil and Australia and European countries where they have to meet harmonic voltage limits, and they do grid studies, and the studies are always conservative and they always show harmonic filters are needed. So they end up putting harmonic filters in all their plants. I don't think we want to get to that. I don't think we want to spend extra money on harmonic filters if we don't need to. And I think it's been proven that probably 90% of the plants do not need harmonic filters, and probably 50% of the plants even have capacitor banks, and they still only a very slight fraction of those need harmonic filters. We're working on the IBR modeling. We're trying to get the right answer to our studies, and we're working on grid impedance so we can understand the effect of these plants on the grid, and that's particularly important with larger plants and offshore plants. So I'm done. That's my presentation. Thank you for your attention today. It's been my pleasure to share these concepts with you.
Thank you so much, Dave. Okay, so we'll transition to Q&A, and we stop the recording from